Okay, so the particular example that I'm taking is from medical sciences. Practically every profession there is would use statistics and statistical inference for operations. Okay, the question that we're looking is, so there's something called proximal humerus fractures in the elderly. Okay, we're not concerned with what it's called. Let's simply say problem in shoulder. This is something to do with issues in shoulder in the elderly. Okay, now in medicine there are two treatments for this issue. One is operative and the other one is through physio. Okay, so you have some data on this. Is this going fine? I think so. Okay, so we have data on 200 elderly people who've gone through treatment. 100 of them have gone through operative treatment and 100 have gone through physio only treatment. So we have total of 200 people. Okay, now the way we have managed this data is we've gotten clean figures on improvement and no improvement. Okay, now we're not concerned with what this is. Doctors would tell us what is considered as improvement and what is not improvement. Okay, after 6 months of the treatment. So the figures that we have is for operative procedures, 62 out of 100 patients showed improvement and 38 showed no improvement. And for physio only, 48 have shown improvement and 52 have not shown improvement. Okay, now different patients react differently to medical procedures, so there's a lot of randomness. Obviously, operative procedures are going to be a lot more expensive than physio only, and these are elderly. They don't want to get under the knife that easily. So, do we look at this data and say that there is evidence that the two are different? The outcome of the two procedures are different. Okay. Now, it's not something that we can simply say. Just like one example, data is slightly in favor of one may not statistically mean that they're different. For that, we'll use the concept of hypothesis testing. Now, we've done one-tailed for the coin toss. Let's do two-tailed for this. Okay. So, what we would take is theta in this would be the difference of proportion of patients which showed improvement. Let's say P sub 1 is the proportion of patients which showed improvement when they went through operative procedure, and P naught for physio only procedure. So theta would be then P1 minus P naught. Okay, this is theta. And if we are testing for differences in outcome, our null hypothesis would be going to start by assuming that there is no difference. So theta is 0. They're same in population. It's just the sample that's just slightly different. If we're testing, if the question that we're testing is if there's any difference, then our alternative hypothesis becomes not equal to 0. It's just this, it's not just the sample, they're different in population as well. Okay. Now let's draw the density function for sample differences. Okay, this is for testing for population, but we're going to use sample for this purpose. Okay, now let's just remind you, although you already know this, theta would be parameter. This would be for population, this would be a statistic, and the general notation for statistics is we just put a caret on top of it. Okay. So, and we're going to draw this distribution by assuming that this is true. If this is true, then our expected value for sample difference should be 0. Okay. Now, I've just drawn this as a normal distribution, but I've not proved it till now how this would be a normal distribution. Okay, let's start with, okay, let me just tell you. Till the time we have such data, this is going to follow binomial. Okay, and statisticians love CLT. Okay, this was in the text that we referred in the 4th chapter. Okay, the moment our data sample becomes large, binomial tends to normal. Okay, so we're just taking that approximation. So 100 is a large enough sample to have binomial becoming normal. Now find this would be 0. Now we also need variance for this. How do we get variance for this? Variance of this statistic would be variance of, yes, okay, and we're assuming that the two are uncorrelated. This is again an assumption that we're starting with. Variance of the proportion is P1 1 minus P1 by the sample size plus P0 1 minus P0 by sample size. This is for operative procedures, that is for physio only procedure. Okay, and I said that we're going to draw this distribution by assuming that the null hypothesis is true. If this is true, then the two are equal. Then we can simply do away with the subscripts in proportion. This would become P into 1 minus P into 1 by N1 plus 1 by N0. This would be the variance. Okay, now if we're drawing this normal, normal has two parameters and we now have both of them. So we'll say that the distribution of this statistic follows normal distribution with parameters 0 and p1 minus p1 by n1 plus 1 by n0. Okay. Now if we have these two, we can draw a normal distribution. We know where it's centered and we know how it's going to be spread out. Okay. The next thing that we need is we need to set what we call in statistics as the level of significance. Okay, so the area under this curve would be 1. It's a density function. Now what we need to select is, the aim here is to select critical value. And where do we get our critical values from? We get our critical values from level of significance. Okay, and statistician love this to be 5%. There is no reason at all why this should be 5%. It's just a practice that we've gotten used to. Okay, in terms of ratio, this would be 0.05. And if you're doing a two-tailed test, so what we should have is, we should have our critical value positioned such that the area here and the area here, this should be 2.5%, 2.5%, together 5%. Okay, after choosing our level of significance and figuring out where our critical value should be positioned, this is the last thing. You select this point and this point as critical values. Okay, sequencing is very important. This should be in this very sequence. You figure out what your null hypothesis is, what your alternate hypothesis is, then you figure out the distribution. We say that this would follow binomial. If our sample is large enough, this is going to follow normal. Then we figure out what are the parameters of this distribution so that we can draw this distribution. It's normal, so we need to know where it's centered, what's the variance or standard distribution. Then we set our level of significance. If it's 5%, then we know for normal how this is going to be. It's going to be 2.5% in one tail, 2.5% in another tail. This would give us critical values after this procedure become residual. Okay. Now, let me just make some space. As we studied in statistics, standardization is a tool which facilitates such analysis to a great extent. Okay, so now let's start studying the test statistic. What is test statistic? Test statistic is standardized form of this thing. Okay. Now, if we have our sample statistic following normal distribution with all this, and let's say our test statistic t, this t is not this t, this t or this t, they are not related to the t distribution as of now. This t is only for t here, test statistic. Okay, you might as well use any other notation for that. The difference between capital and smaller would be, capital would say that smaller is actual calculated value and the capital is for distribution. Now let's standardize our sample statistic by dividing it by the standard error of itself. What would this be? This would be theta caret divided by standard is the square root of the variance of the distribution of sample statistic. This is what we have. Now, if our sample statistic is centered on 0, our test statistic would also be centered on 0. This distribution will also be centered on 0. So what we would have is, we would have expected value of our test statistic also at 0. We need a distribution for this. Okay. Now we need variance of test statistic. I'm running out of space, so can we do, let me not rub this, let me use this small space for this. We need variance of t, which would be variance of p1 minus p1 by n1 plus 1 by n0. This is just a constant. Okay, after you've calculated this, it becomes a constant. This is going to come out and it should be squared. So what we have is, we have p into 1 minus p to 1 by n1 plus 1 by n0, and then variance of, okay, what is variance of this? This is this itself. So variance of our test statistic is 1. What we have with all this is, we have established that our test statistic, which is the standardized form of our sample statistic, this our sample statistic was normally distributed, so our test statistic will also be normally distributed. Okay, with parameters expected value equal to 0 and variance is equal to 1. This is what we are trying to aim at. We were trying to get the standard normal distribution. After standardizing it, then this process becomes easy. Okay, so we can say now that our test statistic, let's get everything, make some space. Defined as this follows normal distribution with parameters 0 and 1. Okay, now not going to draw this again. I'm just going to say, now this distribution is not for sample statistic. Now this distribution is for test statistic T, which is also centered on 0. Yeah. Now, if this is not just another normal distribution, like if it was standard normal distribution, then what we can do? Then it becomes very easy to find these critical values. We just look at the table, and we've done this so much time, so now we remember what is this going to be. It's going to be 1.96 and minus 1.96. Okay, now we already have data. Now this is ripe for testing. What do we do from here? We calculate the value of test statistic. How do we do that? We do that, and I do need space. How this is going to go away. Let the table remain. I'm doing this calculation with blue. The smaller case t would be for actual calculated value. And this calculated value now would come from the sample, so there will be a caret on top of everything now. We have these values from the sample. This is 0.62 minus 0.48. Okay, now at all times the distributions are being drawn assuming that the null was true. If the null was true, we're going to put 0.5 and 0.5 over here. Then we have 1 over 100 plus 1 over 100 squared. This is going to give us value 1.99. There's a point here. Okay, now after getting this calculation done, we're going to see where is this 1.99. It's slightly, just slightly to the right of our critical value. It's in the rejection region. Sorry, 1.99. Okay, and what you also need with this is you have to make up your mind. If it's 5%, it means 5%. That means it means 1.96. That means if it's 1.9625, you reject it. Okay. So what do? We reject this. We reject the null hypothesis that there is no difference between the two. Okay, then they're just different. Mind you, we have not proved at 5% level of significance that operative is better than physio. Not done that. We have just proved that they're different. This is what we aimed at doing. If we have to start with alternative hypothesis that this is better, it should be one-tailed, then it will be slightly different. Although I would claim here it's easier to do that. Once you have, you're going to get that, but till this moment we have strictly technically speaking not done that. They're just different.